All right, so good morning, everyone, and welcome to those. I know that some people have arrived. So to just briefly summarize, so on Tuesday I introduced some notation and some motivation why we are so excited about quantum computing power, in particular from the perspective of a person whose main interests are in developing solvers for challenging applications. And in particular, I talked about perspective from the quantum numerical linear algebra. So I introduced how we input the data, in particular vectors or matrices in a general setup. So a little bit about block encoding. I know it was fast, but I will make sure that you get the slides, and if you have any further questions, please contact me. So today So first of all, there's way too much material here, so don't worry, because there is a certain overlap and I will not try to cover everything, but I will just leave the slides such that it's kind of coherent with respect to what I think is essential and what you may find helpful. So you will see that I will start skipping things because you have learned already about quantum Fourier transform, so it's one of those essential tools that we are going to use in different settings in the quantum computing. So I'm not going to talk about that, but if you want for the reference, you can go back and look at the slides. One thing that I would like to just shortly mention, which you will see, and I briefly talked about that last time, is linear combination of unitaries, or the LCUs. So remember when we were talking about inputting a data like a matrix, the first challenge was how do I turn a matrix which is not necessarily unitary, or the operator which is not necessarily unitary, to something which is unitary, because that's the only object I can work with. So we talked about so-called block encoding, how we can take arbitrary operator, arbitrary data matrix, and embed it into something which is a unitary operator to encode our data. But there was a second step, which was, okay, from there, I have my unitary operator, but I have to turn it into the circuit. And we discussed the cases where getting a unitary operator was kind of straightforward, but that straightforward path led to the quantum circuit, which was quite complicated. It was long, so for the not fully fault-tolerant machines, the longer the circuit, the more error and noise we have. So, and we also learned that those unitary block encodings are not unique. So we have choices, but we have better and worse choices. And so one of the things which is also becoming a part of it is, if you have a few block encoded matrices and you start to combine them, or you have a number of, you have a unitary matrix that you want to decompose into the sum of unitary, or maybe not a unitary, that LCUs cover also. You want to find the closest unitary approximation to your matrix. And this is done using the linear combination of unitaries. Unfortunately, I will have not much time to go into details here, but it's a very important tool. As you will see, there are two essential results which were basically introduced in Kotare's PhD thesis. It's a very nice written thesis, so if you want to read in details about LCUs, I recommend going to that resource. So if you have a so the first one is exact LCU. So if you have a matrix, how to decompose it as a linear combination of unitaries. And then when you have a linear combination of unitaries, we know, and usually simple unitaries, how to encode that, how to move it into the circuit. And then the approximate LCU algorithm is what we very often have to do in practice. So we know when the matrix is delta close to some unitary, and we want to express it as a linear combination, and there are results telling us how we can do it, how expensive it is, and what we need in terms of tools. So when we have the LCU lemmas, which we then use those results to actually build a circuit that allows us to do the linear combination of unitaries. And you can think about it from the point of view of standard linear algebra. You want to build the linear combination of some nice objects in the very nice spaces such that you can work with those nice elements. And in the paper by Barry and the collaborators, they actually used, they show how you can get the block encoding of the LCU using more complicated than the simple gates. You need the select oracle and prepare oracle. And the cost associated with that is proportional to, of course, the ancilla qubits that you're imposing, that you need to block encode every of the elements. So these are the two results, again, in terms of building a circuit and turning it into practical. Those two papers here by Barry and Coulthers and Gillian are the resources that you may find useful. And as I said, there is a lot of theory that says that the number of ancilla qubits is, unfortunately, depends algorithmically on the number of terms. So of course, the longer your linear combination, you may need more ancilla qubits, so you see it in the complexity. The other thing is you need a multi-qubit controlled unitary operation. So there's select and prepare that are more complicated than just simple gates. And there is a very recent paper on implementing any linear combination of unitaries by, I'm not sure how I should pronounce it, but Chakrabarti, maybe? I'm sorry for mispronouncing. It's a very interesting paper about how to turn it into really implementing it in an efficient way. You learned about quantum phase estimation yesterday, so I'm not going to talk about it. Another important tool in all the aspects of algorithmic quantum computing, quantum algorithms. So eigenvectors are important, and eigenvalues in terms of application, but also in terms of tools for another building blocks. And you can achieve it in a different way. You did some lab implementations yesterday. There are different approaches. You see the QFT is immediately appearing here as a tool, the Hadamard test, and then the Kitaev method is also like Kitaev was heavily involved in developing those algorithms and the methods, so that's his approach as well. Quantum phase estimations, the same. Also, I think you have seen that multiple times already, but just for the state of coherence of the presentation, you also have it here if you want to go back. So what my goal will be today is focusing a little bit about the quantum numerical linear algebra problems. So looking on the problems that we are interested in numerical linear algebra and scientific computing in general, and talk about how we can tackle their quantum counterparts, what are the tools, and what is available at the moment. So from the point of view of applications, fundamental problems in numerical linear algebra, for those of you who have any background, and if not, you can always ask me after. There are several classes of problems, and we can discuss if these are all or not, but this is kind of the standard problem set if you open any linear algebra book. So you first learn to solve linear systems. So given a non-singular matrix, you want to solve AX equals to B. Okay, the most simple problem, but as you know from many of your own applications, there is a long way to go from your real-world problems, turning it into something as simple as a linear system. But then, for some of you, the path ends there. You turn your complicated model, your complicated PD into something as like gives you maybe a linear system at the end, and that's your job is over, and then that's where people like us step in to say, okay, how we can do it in an efficient way, and not just take a black box approach and then figure out why that doesn't work. And believe me, we have a lot of situations where practitioners come to us and say, we took this algorithm from this book for this problem and it doesn't work. And then it's like, well, because this algorithm is not proper for your problem, okay? So there is still work for us to do. So then the solving least squares problem, another instance that you all probably know very well, if not from the linear algebra, then from machine learning context. You have the matrix and the vector, but you know that there is often either no exact solution to AX equal B, or there are infinitely many solutions, or you are interested in some particular solution. So this corresponds to minimization problem. Here I say, okay, I want to find the x that minimizes the norm of the error, so ax minus b. In some particular norm, for me, it's 2 norm. Another class, solving eigenvalue problem. So here we turn from linear to nonlinear. The eigenvalue problem is a nonlinear problem in a sense that you know that the eigenvalue depends on the eigenvector. So it's very different setup than the solving linear system, although the tools from solving linear systems are used as a building blocks in many eigenvalue solvers. And a very general class, which actually you can turn the other problems into the problems of functions of matrices. So this is not usually a standard content in the like most general numerical linear algebra class, but it's very, very important from the point of view of studying dynamical systems. Actually, any of this previous problem can be turned into looking on the function of matrices. So you evaluate a function which you define for the scalar values for what does it do if you want to apply it to the matrix. So I will start with functions of matrices because these will allow us to introduce the concept of qubitization, which we'll need later on for, in particular, Krylov subspace methods, so methods of solving eigenvalue problems. So matrix functions, and here I'm going to talk about Hermitian matrices because the formulations are much easier. So I will have a Hermitian matrix which I can diagonalize. And as you see, a lot of problems can be turned into that problem. So if I want to solve a linear system, you can say, okay, this is the same as evaluating function of A. This function is the inverse of A for non-singular matrix and applying it to vector B. And then I will get the solution of the linear system. If you're interested in more application-motivated problems, Gibbs state preparation, it is a function of matrix. And then what you may ask yourself, what that means. Some of you may have seen functions of matrices. What does it mean to take an exponential function of when the argument is a matrix? And Hamiltonian simulation, another object which you have seen already on Monday. So the goal in dealing with matrix functions, very often, as you see, for example, here, it's not just applying the function to the matrix, but actually being able to calculate this quantity. So in terms of linear algebra, applying a function of matrices, applying it to the vector. In terms of a quantum is construct an efficient quantum circuit that can compute this quantity, which is just applying matrix vector or operator function to the state for any available state. And you want to be able to do it in an efficient way. And one of the ideas that I will talk about to evaluate matrix functions is due to the early paper by Lo and Chang. It's the idea of qubitization. And I will try to explain it. We'll see if I succeed. And if there are any questions in the meantime, please interrupt me. So I will start with the definition in the most general case, well, in the most easy case, so the case of a Hermitian matrix. What is the function of a matrix, or how you define the function of a matrix? So we can think about this in terms of classical matrices and vectors, but you can think about qubit operators the same way. So you have a operator, so n-qubit Hermitian matrix A, and you have its eigenvalue decomposition. So you have the eigenvectors and the corresponding eigenvalues. Here we will assume that the matrix is Hermitian, so the eigenvalues are real. And you try to evaluate a function which takes reals into complex. So this is a scalar function such that you have to make sure that your function is defined at each eigenvalue of this problem, because that's the essential component that we need. And there is a long discussion how you know it in advance and things like this. But if you're interested in matrix functions in particular, there is an excellent book by Nick Hyam about functions of matrices. It's a SIAM available book, and you can find all the details. So when you have an eigenvalue decomposition, it seems to, it actually works very nicely for us. So you need to be able to evaluate the function of the eigenvalues, because actually your function of the matrix will be defined quite nicely, and it's very easy calculation that it's essentially you use the eigenvector matrix, and then you use the function of the diagonal matrix. So this is f of lambda, where lambda is the diagonal matrix with the eigenvalues on the diagonal, and this diagonal matrix has actually evaluations of the function f at each of the eigenvalues. That's why they have to be defined. So this gives you, of course, a matrix, and the result is a matrix. So the function of matrix of a matrix is a matrix object. Okay, so now it's going to get dense, and I will try my best to explain it. Where is Misong? Misong is there. Okay, Misong, in case Misong will let me know that it was too fast, too complicated, and so on. So I will look at you, Misong. So qubitization is an idea of representing matrix functions. So how we can take the idea of matrix function and move it into the quantum world. And in particular, because of many applications and the context of a Krylov subspace methods later, we will be very interested in very particular matrix function. We will be interested in evaluating polynomials, and not any polynomials at this point, Chebyshev polynomials. So just for those of you who, and I will go through that in details, but I hope that these objects are known to you. If you're not, Google it, Chebyshev polynomials. These are the Chebyshev polynomials of the first kind and the second kind. These are nice orthogonal polynomials, very powerful, used in many applications. Even if you haven't taken classical numerical analysis stuff, I'm pretty sure when you are doing anything connected to physics, quantum chemistry, and so on, you have seen Chebyshev polynomials. If not, never too late to learn. Okay, so let's just try to look on the very simple idea example, and step by step how what is the main idea behind the qubitization and how it's realized. So let's just assume that we have lambda, a parameter that is between -1 and 1. This is because of the definition of the Chebyshev polynomials that we have to have that range. And we will consider a 2x2 rotation matrix. And here comes the short comment. If you look in the literature on qubitization, sometimes you may see the signs flipped here. It's not that someone is wrong or something, it's because different communities use different rotation, sometimes counterclockwise, sometimes clockwise, and that affects the sign. So it's the same thing, and then your matrices may be on one side or the other, but that's just stay with the rotation matrix which you want, and you can derive it the same way. So we will introduce this rotation matrix. So let's call it rotation operator O of lambda, which looks like this in terms of lambda. And then when you do the change of variables, you say that lambda is cosine of theta. Then obviously, you'll end up with this matrix, which is what you have learned as a classical 2x2 rotation matrix. The nice property, if I take the kth power of this matrix, due to the trigonometric properties, you will get this object. And then if you go back into your lambda definition, we get this matrix, which has a very, very nice structure. In a sense, what is sitting here is the kth Chebyshev polynomial evaluated of lambda, and some other stuff. Or I mean, in this case, we also have the Chebyshev polynomial here. But what is important, this is how I get, using rotation matrix, applying it in the powers, I will get evaluation of the kth Chebyshev polynomial at lambda. Okay? So the goal for us is, I said, okay, we want to evaluate functions of matrices. In particular, we want to evaluate the polynomial of matrix. And I want a Chebyshev polynomial. So my goal at the end is I would like to have here the Chebyshev polynomial, the kth Chebyshev polynomial applied to A. Not a scalar lambda, but a matrix. So how we can do, so because if I can do it, I will immediately get a 1-1 block encoding for the Chebyshev polynomial tk of A. And that's the object that I want. Okay, so now how we can, use this idea of having the rotation matrix and get the object we want. Is the goal clear? Are there any questions here? Okay, so let me move. All right, so in here we will assume that we can query the matrix in exact block encoding model. So I will assume that I have an access to one M block encoding of a matrix A. So we're just as a reminder, UA is a unitary matrix, and it's one M block encoding, meaning that there is no error epsilon. So if I use this encoding and I look on the definition up to, there is no error if I measure the discrepancy between the object connected to my block encoding and the matrix A. And one is alpha, so it's like the parameter that I assume that the norm of matrix A is bounded by 1. And now I consider the eigendecomposition, so the object which we have seen written in the Dirac notation. So this is nothing else as a linear combination, right? If you look, this is linear combinations when the coefficients are, the eigenvalues are here. You actually have what we call rank 1 matrices, which are the projector corresponding to the eigenvector. So following a definition of the block encoding, since I assume that it's exact block encoding, this is the relation between the block encoding and the exact matrix A. So for each of the eigenstates, Vi, I can look on this object. So I can apply the block encoding into this Kronecker between the the state that was connected to the ancilla qubits and the Vi. If I do this calculation, so first I use the property that this is, of course, the block encoding, UA is block encoding of A. So that gives me the first part. And then I get some extra part, which is the unnormalized state orthogonal to all states of this form. In a sense, I'm doing the decomposition of the vector into something into direction of the vector on arbitrary vector in the direction of the eigenvector and the orthogonal direction. So the classical linear algebra decomposition. So if I do that, okay, I will get, so this is the same vector, right? The same object, the same state, the Kronecker of these two states. This is the lambda I, and this is just the this unnormalized state. Meaning that if I use the projector operator, this projector operator, and then apply it to this state, I will get 0 because it's orthogonal to that state. One can also normalize it, and that's somehow very often how you will see it. Instead of this perp tilde, you get 1 minus lambda I squared perp I, not tilde, and this is when you use the normalization. And this is an easy calculation, just following the definition of the and the properties of the unitary and the properties of the block encoding. Questions? All right. Okay, so now if I replace this unnormalized state with normalized state, I get this one. And you can see that you actually are already having a particular basis of your Hilbert space associated with this problem, but I want to simplify it. I will now identify this state. So this is the Kronecker of m copies of the 0 state and Vi as 1, 0. You can always do change of basis in the in the way you want. And I will say that this perp I is just a 0, 1 state. I want to work with standard basis because for the purpose of presentations, it's way easier. Okay, so now I will, if I do the calculation from before, let me just go back. If I look on this, I apply UA to this object, which I now denoted by 1, 0, and I use the following definition. So I have this. I know that this is 0, 1 in my notation, and I also know that this is lambda m times 1, 0. So just plugging in everything. I know that my block encoding UA applied to the 1, 0 vector gives me this vector. I also know that UA is a unitary because it's a block encoding, so it's a unitary matrix. And here we assumed also it's Hermitian. Okay? So I know that U squared A has to be equal to identity. I already have the first column of it, so then I can easily get back the formula for this matrix. So this matrix is, the block encoding UA will have this form. Right, so if I apply it to 1, 0, I will get this one, and the other part is this. If you look on this, this is nothing as a reflection matrix. You can again do this swap of variables to have it in terms of cosine and on sine, but this is the reflection matrix. So the block encoding UA is a reflection matrix. Okay. So this is this. So remember, our end goal is to get the block encoding of the Chebyshev polynomial evaluated in matrix A, and this was possible using the rotation matrix, OA. So in power, OA was the rotation matrix to the power K. If you look on this object, it's almost there. It almost looks like a rotation matrix, but it's not a rotation matrix exact. So now our goal is how we can actually, what type of transformation we have to apply to this to get a rotation matrix, because if I get a rotation matrix, then I can get my Chebyshev polynomial evaluated in matrix A. Okay, so for this 2 by 2 example, I can easily figure out, and this has to do also with change of basis and reflection, it's a general statement, but I have my reflection matrix. I need to apply something to it such that I will get my reflection matrix. What matrix R pi I have to apply to it such that I get my rotation matrix O? Well, it turns out that I have to apply a matrix of that form. Okay, so if I do it, I will get my rotation. So using the R and the block encoding of matrix, I can get my rotation matrix. This is by 2 by 2, but the idea is more general, we will see it. And of course, if you look closely what this R is, This is associated with the projectors. So essentially, the projector that I defined before, and so it acts as a reflection operator restricted to the subspace that you're working with. So in our case, it was just simple 1, 0, 0, 1 basis. So now I know that my rotation matrix can be written in times there should be r pi, sorry, I just dropped the pi here for simplicity. The matrix R, which has the structure 1 and -1 for 2 by 2, we'll see the general instruction soon applied to my reflection matrix, which is a block encoding to the power k, that gives me the object I want. I will get this evaluation of the Chebyshev polynomial at matrix A and some other stuff, but the other stuff I don't care. Okay, so this is 1m block encoding of the Chebyshev polynomial. So if m is equal to 1, so this is the number of ancilla qubits, then this r pi is just a Pauli Z matrix. So this is how you can build this operation for a trivial case m equal to 1. So you can implement this transformation using signal qubit. However, usually we don't want only m, so we have to go to larger number of ancilla qubits because it's connected to also the input. So the circuit, if we want to apply the general operator O, and we have to repeat the circuit k times. So that will be the circuit for one step of qubitization with Hermitian block encoding of the Hermitian matrix. So this is the block encoding of your matrix, and here you apply m times the operator, or k times your rotation operator, and if you do that, you will get the block encoding associated with the Chebyshev polynomial. Let me go back, sorry. So in summary, we can use rotation matrix to get the Chebyshev polynomial evaluated on the matrix of interest. In order to do it, we need to connect how our block encoding can be turned into the rotation matrix, and we can do it by this additional operator R, which is actually also like reflection with respect to the Hilbert space, so with respect to the bases that we have been working with. And we will see that idea in application in a moment. Yes?
It went pretty fast, so just to be sure I follow.
Yes.
Every time you apply the Z parts, you elevate OK by 1 power of...
Yes.
So if you want to OK, you apply it k
Yes,
times?
you have to apply it k times to get your rotation operator to the power k, because you need that rotation to the power k to get this. If you get it only to the power 1, you will get the first Chebyshev polynomial evaluated A. If you need the kth Chebyshev polynomial, you need to do it k times. So it depends on the index of the Chebyshev polynomial you need.
The part I didn't understand is how can we do it before applying the block encoding and it still gives you the power k?
That part we will get to that. So we will get to that. I just need the idea of qubitization, and then for the particular Hamiltonian, we'll look how this kind of boils together, because it gets a little bit tricky how you can do it in terms of circuits and so on. But here the idea is, so just to go back, sorry. Here the initial assumption is that you have an access to the block encoding. So the other part will be how to incorporate block encoding procedure into this, and we will talk about that later. If that's not clear later, just ask me after. Yes?
So is there any post-selection in the procedure? So, or do you get directly the O of k theta in k times without post-selection?
Oh, yes. So
is there any post-selection involved? So do you need to measure the ancilla qubits to make sure you get the right answer?
So the question was if there is the measurement of the ancillary qubits. No, there is no at the moment. As I said, we will see how the procedure connects when we have the block encoding involved, and that I think will clarify. But for now, it's just we keep it as simple as possible. Okay, so since I wanted to talk about many problems in linear algebra, I will just briefly touch on linear systems. Is Nana here? Okay. Oh yeah, you're here. So just a brief intro to linear system. So one of the classical problems, linear system solvers. So as I said, we know what is the idea in the classical sense. And I'm talking here about, for simplicity, the matrix A to be Hermitian. So you want to solve a linear system. We know that the most general purpose algorithm for the case of Hermitian matrix is conjugate gradient method. So those of you who are familiar in the iterative solvers, if not, again, I will do a recommendation on excellent books by Youssef Saad, available online, available from Siam, available from his websites, even as a PDF. And the conjugate gradient method has asymptotic complexity O of n. So remember, n is connected to the number of qubits. So the size of the matrix, square root kappa of A, kappa is the conditioning. So it's connected to the condition number of your matrix. So if your matrix is badly conditioned, then of course it goes into complexity and obviously the size. Okay, so what is the equivalence in the quantum world? In the quantum world, we want to solve the similar problem given n-qubit matrix A and a quantum state B. We want to find, or more precisely, we want to prepare a quantum state, and I will call it x tilde, such that we want to minimize the discrepancy between the state that we prepare and the exact state, which of course we don't know. And we have some tolerance that we're interested in doing that. So x tilde will be called the epsilon approximation of the quantum state. And we know that in exact, if we can do it exactly, if we can actually solve it, then how the x can be defined. So it's the inverse of our operator applied to x, and then we have the normalization procedure. So this is kind of, theoretical. Theoretical part. What are the assumptions of using quantum linear system, solving quantum linear system problem? So you assume that there exists a black box procedure to compute the elements of the matrix A. Can be block encoding, and can be the other ways of accessing your information, as we saw how to encode the sparse matrix. But you have to be able to access the elements of your input data, obviously. And there is also a black box procedure to prepare the initial state. So the same problems which we discussed yesterday, you have to be able to input your data. So you need a state preparation procedure, and you need some kind of block encoding or equivalent way of representing the matrix. And we assume that they both have to be implemented using the two qubit gates in a constant time. So that's an assumption. We want to simplify the circuits, and constant times means essentially it's doable. It's not that you're going to wait forever to input your data, because then there is no sense in doing any simulation. So the number of uses of this procedure determines the query complexity. So the number of uses, the number of times you will have to do the state preparation and access the entries of the matrix that will connect to the complexity of this algorithm, and it also provides a lower bound for the gate complexity. Okay, so there are some assumptions which we have to be take into account. However, there is one thing which you have already probably also seen in other talks is, since it's a quantum version of the problem, it's not that we will get the solution vector as a vector and we are like, great, this is what we have. It's actually computing the expectation values in the solution of the system. So it's not as straightforward as in the classic case that you get the vector and I have it. You get it in terms of like other quantities, and in particular, here you have the expectation value, so not like a vector itself. Okay, so there has been a lot of results on query complexity for quantum linear system problem. The initial result, which is also connected to the algorithm that I briefly discussed, so Hasidim-Lloyd or HHAL algorithm, as it's often called. It was introduced in 2008, and it used quantum phase estimation. That's why quantum estimation, phase estimation is one of the basic tools. Then in 2012, there is a variable time amplitude amplification algorithm, which, as you see, these are all complexity results and different algorithms which achieve different complexity. Then there is a paper from 2007 that used the LCU and Chebyshev approximation. So you use the linear combination of unitaries and then Chebyshev polynomials, and then you can solve your linear system using Chebyshev polynomials, because if you think about classical conjugate gradient method, for those of you who have seen it before, it's actually connected to orthogonal polynomials. So Chebyshev polynomials are optimal choice of basis in terms of conjugate gradient method. So it's not a surprise that Chebyshev polynomials are appearing here. Adiabatic quantum computing, it was, you have seen a lot of that on Tuesday as well. So they're using adiabatic quantum computing, you can also do the linear system, solve the quantum linear system with the according complexity and time optimal adiabatic quantum approach. Remember, there is always something to optimize, either the time or the gate length, depth, or whatever, depending what your objective is, the best in terms of that objective may be different. So I just briefly want to introduce the HHL algorithm. This is actually, it's 2008, but it was published in 2009, so I'm giving you the reference to the published paper. So prepare a quantum state whose amplitudes are equal to the elements of the vector x that solves the AXB for symmetric positive definite. Okay, we need symmetric, we are talking about symmetric positive definite matrix here because the assumption for this is that the eigenvalues of the matrix A are not only real, but they're actually also positive, and that involves the structure for this particular application. So the HHL algorithm is the first quantum algorithm for solving quantum linear system problem. It gives, as I told you, the scalar measurements on the solution vector, not exactly the solution vector in the classical way. Implements 1 over kappa A approximation to the initial state. So kappa A, it's not a surprise that we see the condition number of A here. We see it in the classical estimate, so for CG, that the accuracy up to which you can calculate your solution is determined by the conditioning of your problem. It's a standard result in error analysis for solving linear system, and the complexity is also connected to the conditioning and the accuracy up to which you want your approximation. So, for example, it can be of order kappa squared logarithm of n divided by epsilon. So remember, kappa is the condition number of matrix A. You cannot change it. Your matrix is conditioned. It's like a property of your problem Then you have the log of n, it's a size, and then the epsilon is the parameter you can tweak because that's the quality of your approximation. Okay, so we assume that we have a matrix which is non-singular. We assume that its condition number is finite. It may be large, be careful. And we have the eigendecomposition, which we have all the eigenvalues encoded with using d-bits representation. That's the only thing relevant here. So how the procedure looks like, and it's very simple to describe, it's not so simple to implement. And so the HHL algorithm is implemented in Qiskit. You don't have to implement it, you can just use it. So first is you use the Hamiltonian simulation techniques which you learned on Monday to transform your matrix into a unitary operator. So you can do it in this way. That then you can apply to B. Remember, like everything, if we think in terms of you have access to apply the operator to the state. So that's the procedure which you have to be able to do. And you have to, in a classical way, if we think about the iterative algorithm, which we try to mimic, is that we always want to have an algorithm which only uses like matrix vector products. So you have to be able to apply your matrix to the vector. So here we want to be able to apply our operator to the state. So if your B is an eigenvector, then it's a trivial implementation. You can use the quantum phase estimation, which you can create the unitary UQPE such that you apply it to the vector, but since it's an eigenvector, of course you get the result trivially. If it's not, then you want to expand your input state in terms of the basis, some basis. Remember classical trilinear algebra, we want to expand vectors in terms of very nice basis vectors, which we have, and we do it here in a similar way. And the nicest bases in this setup are the eigenbases. Okay, we question how to get them and so on, but if you can do it, we assume that we can expand the input state in terms of the eigenbases, then essentially applying this unitary operator to the vector. The result is given by just taking a linear combination and some scaling factor here, which we'll see in a minute. Okay, and then, all right, I want to be, you remember we assume that we are able to apply the matrix to the state. If I do it, so here I have to have an access to the inverse. So this is also, you can build the query for block encoding for this. If I apply it, well, I will get, this is my solution. So you need to use the information of the eigenvalues, which will be stored in ancilla register. That's why you need, since we don't have a possibility of copying things whenever we want, we need to deal with ancilla register. And you have to perform a controlled rotation to multiply the factor to each beta j. What is happening, you get your summation in terms of beta j, which you have from previously, but you have to still be able to use this multiply by 1 over lambda j, and you have to do it in a clever way, and then it uses the rotation again to just apply the scalar factor. So the idea is very simple implementation. It's a more tricky way. There are a number of articles how to implement this algorithm. If you have time, and that's usually the problem. If you have time and you're really want to learn, learning by doing is always the best thing. So, but it requires way more time than. So if you don't need or you are not interested in particular details, just use the Qiskit implementation. If you are interested, try to work with it yourself and then compare. That's always a good exercise. Okay, but my area of research in many aspects boils down to solvers for eigenvalue problems, and that's why I wanted to talk about that, and I will see how far I can get onto this. So if you think about classical eigenvalue problem, as I said, given Actually, that doesn't, copy paste. It doesn't have to be non-singular, but we will assume Hermitian. So given a matrix A and the vector, and again copy paste, sorry. Given a matrix A, we want to find lambda. So if it's a Hermitian, we know that the eigenvalues are real. So we want to find the lambda in a non-zero vector such that Ax equal to lambda x is satisfied. It's classical eigenvalue problem. We will talk about a specific example which you have seen already Monday and Tuesday, Hamiltonian simulation. So we will look on a specific problem and then we will use the tools to just illustrate. So given a Hamiltonian, which you can think it's a given a matrix or an operator, and this Hamiltonian is very particular, it's just a linear combination of Pauli matrices. We make an assumption that there is normalization, so all the alphas actually here will be positive. They sum to 1, and the sign of the Pauli will be in the pi component, and we will try to approximate a ground state. So the state corresponding to the ground state energy, so the smallest eigenvalue of the Hamiltonian. You have seen this problem several times already, but I want to demonstrate the technique, so I need some example that everyone is familiar with. So is the task clear? We want to calculate the eigenpair or I don't know how you call it, eigenpair state, eigenstate pair? I don't know. I don't know if there's clear definition of that. And we will start with the idea of quantum subspace diagonalization. So for those of you, and there were few, who had some experience with numerical linear algebra, we will try to do something which is connected to projection methods in numerical linear algebra. In particular, here it's called subspace diagonalization, but it's a very similar concept. So what is the general idea? So I will explain that in details here, but you can think about, first let's think about the classical problem. You have a huge eigenvalue problem, Ax equal to lambda x. It's so huge that you cannot even put your matrix A into the computer, but you know one thing. You know that there is a way for you to apply the matrix into the vector. And some people say, if you cannot stir the matrix, how you can apply it to the vector? Okay, there are a number of techniques that will give you the access to matrix vector product without the matrix specifically. So it's a huge problem. So the projection idea is the following, and there is a lot of theory in that. Let's assume you will pick a finite dimensional space of certain size, which is reasonable. Reasonable in the sense that you know that you will be able to, for example, store the number of vectors. I guess I call it capital D here. So you say, okay, I am able to store maybe 150 vectors in my memory. So I will choose the subspace of size D. Okay, so the idea will be, can I project my giant problem into that subspace and then work with the small problem that I know how to handle? So the idea is quite simple, but there's a lot of components involved. How to select the subspace such that actually, if I was interested, in my case, I'm interested in the lowest eigenvalue of this big problem, such that my lowest eigenvalue can be extracted from the small problem, and they actually are a good approximation of the one from the larger problem. So how to select the subspace, how to generate the basis of that subspace, how I can work with. What do I do when I project the problem on the subspace? So it will be a small problem, but it will have various properties. And what can I expect from the error? And that's a whole week course on projection methods and so on. So But the general idea is how I can take a big problem and turn it into a small problem, and from small problem I will get an information on the big problem. The simplest idea. So that's the idea behind what we call projection or subspace projection methods. So in terms of quantum, let's assume you have given a set of states, phi k, and okay, we know we need some way of preparing those states, so we will have quantum circuits which correspond to the, of course, unitary operators, and we will have some initial state. So I will need initial state and ability to apply a unitary operator to it to define some additional states. And in particular, I will need d of those states. So in other words, I will have to be able to prepare states phi 1 to phi d. So these states I have to be able to prepare. And those d states will live in some d-dimensional space, or will define the d-dimensional space. And I will try to project my large problem onto this, my Hamiltonian H. Sorry for the notation, but I couldn't use like bold H for everything. So the Hamiltonian was denoted by the curl H to project that problem. Okay, so how does that work? Okay, in order to project, I will use the states that I have been given, and I do the projection. So I apply in linear algebra from the left and the right. So you will get a scalar. You will get an entry, which will be the entry of the matrix, the ijth matrix of this matrix. So if you look, the dimension, what will be the dimension of this matrix? H, bold H. It will be d by d. And with the assumption that d is way smaller than your original operator. Okay, and then also, in ideal world, when we do projection methods, we want to use orthogonal basis. But orthogonalization is not a procedure that is doable in the quantum computing. So we have additional component. We have an inner products between those bases. These are bases, but they are not orthogonal bases. If we have orthogonal bases, we will have a classical standard linear eigenvalue problem. So it will be hv equal to mu v. This is d by d problem. But since we don't have orthogonal bases, we have generalized eigenvalue problem when this S is the Gram matrix measuring the inner products between the basis vectors. So this is small. This is d by d. Any questions? Yes?
The set of states, it has to be known a priori, or can it be constructed in an iterative process?
So it actually has to be constructed in the process. You see that you start with phi 0. That's the only thing you know, and you have to be able to apply UK.
But all the UKs have to be known a priori.
No, you can give them on the fly. You have to be able, okay, when we think about that, you have to be, we'll go into procedure how it's constructed in practice, but you have to be able to get the access to those entries, and we'll see how this is done using the cubitization idea, actually. Okay, so the remark, S is the overlap matrix. So we can estimate those matrices, and I will show you how can be estimated by doing the entries can be estimated by a repeated swap or Hadamard test. But it's a generalized eigenvalue problem which causes additional difficulty that this matrix S may be ill-conditioned, so we have to you may have to regularize. It's an ill-conditioned small problem, so there is additional component. Because if this matrix is ill-conditioned, then we have to make sure that we are not getting garbage out of solving the small problem. So there is has to be regularized due to unconditioning, especially if the bases are growing. Okay, in classical numerical linear algebra, we also have an issue when the D is longer. At some point, your bases, which should be orthogonal, may not be orthogonal, and then the inner products are not 1 as they should, 1 and 0. That causes the same type of problem. So it's not that it comes only from the quantum equivalence. So how we can now turn this projection idea into the algorithm? And the idea is what is the classical Lanczos method? So Lanczos method is an iterative process. I should have put the citation for the classical. I'm so sorry. I will add that before I set the slides. So Lanczos method is one of the so-called Krylov subspace methods. So it has this projection idea that I mentioned, but it uses very particular subspace. It uses the subspace which is called Krylov subspace. And it uses also, in classical sense, orthogonal bases. But let's assume that we can straightforward try to use classical Lanczos method to solve this eigenvalue problem. So how do we do? So we have our Hamiltonian that I said, it's Hamiltonian H and the initial guess. We have to be able to apply this Hamiltonian to the initial guess to get the set of this initial states or basis states. So if we do that, we create the space. That's what it's called Krylov space. Those of you who worked with iterative solver, it's just the space that you have initial vector and then you apply powers of your operator. You gather those vectors and you have a Krylov subspace. In the classical world, we will get we know how to get orthogonal bases of the space, so the work is a little bit simpler. But even without orthogonality, we can still project on that space getting this H and S. So H is D by D, S is D by D. They're small matrices. Unfortunately, because of lack of orthogonality, we don't have a nice structure. In classical Lanczos, H has a very particular nice structure. We lose that, but it's still a small problem. And what we want is the lowest eigenvalue, or also called Reed's value, associated with this generalized eigenvalue problem, which will hopefully approximate the lowest energy of our Hamiltonian. And this is doable because of the extensive error analysis for what we call Rayleigh-Reed's procedure. So projection idea that we can actually check when it's possible that when it happens that the smallest eigenvalues of this problem are a good approximation to the smallest eigenvalue of our large problem. So the advantages of this classical quantum, if we apply the classical idea straightforward, will be we have exponential convergence with respect to D in infinite precision arithmetic. I'm not assuming that everything is exact on paper. So the larger the space, of course, the more accurate, but the larger the space, the more we have to pay. But with respect to D, we see that since it's exponential convergence, reasonable size D is enough. Disadvantage, if I apply this procedure straightforward, I will run into the problem that storing these vectors is already, and that relates a little bit to the question. We cannot store those vectors. They're too large. So we have to be able to see how we can actually get similar objects or the access to those objects without the requirement of storing these giant vectors, because we get an exponential overhead which is connected to classically representing these vectors if we would like to. So this is not feasible. So the question was, and I will focus now mostly, you will see the reference in a minute, on what's called quantum Lanczos, which was introduced by William Kirby from IBM, who is one of the leading people working on Krylov methods for quantum computers. He asked himself also, is it possible, so people ask themselves, is it possible to design a quantum version of the classical Lanczos algorithm that reduces state vector overcut while maintaining the rapid convergence. So we want to exponential convergence with respect to the size of the Krylov subspace that we know from the classical, but we don't want the exponential overhead because of the storing the vectors. So there were attempts toward what we call now the quantum lunches. So there are several quantum methods that have been proposed to adapt the Lanczos original algorithm. So imaginary time evolution, I mean, we could make weeks of those lectures here, I think. Super interesting idea. Real-time evolution, so Q-Lanczos was introduced within the same group at IBM. Then real-time evolution approaches using what is called quantum filter diagonalization. So here are the reference if you want to take a look. Linear combination of time evolution. There is a quantum power method. So those of you who have a little bit background, Krylov methods are kind of a generalization of the simple idea of a power method. So you apply the powers to the vector, and you can get the smallest or largest eigenvalue depending what you want. There is a quantum version of that algorithm. But Krylov allows you not only to compute the largest and the smallest, you can calculate way more because you look on the subspace not as a single vector. So all these methods converge to the classical Lanczos in specific limits. However, both real imaginary time evolution requires approximation, meaning that they construct the Krylov subspace, which is approximation to exact Krylov subspace in the classical sense. The advantage of the algorithm that I'm going to talk about, which I call truly quantum, or Will also calls it truly quantum Lanczos, is that this will allow, with some assumptions, to create a subspace which is exactly the same Krylov subspace that you will create if you would be able to store those giant Krylov vectors. So the space will be exactly the same, which is a huge advantage because we will get the same convergence properties and the same error and estimates. Okay, so as I said, the quantum algorithm that produces exactly the same Krylov subspace up to finite sampling noise because of details how it's implemented. So the idea will be to apply it to the problem that I showed you. So the Hamiltonian that we'll use will be encoded as a linear combination of Pauli operators. It's because how you can actually do the implementation of the matrix entries and so on. However, you can generalize this method to other block encoding. So you can take other Hamiltonians and use the block encodings because it basically is based on the block. If you have access to block encoding, then you have to incorporate it in the algorithm. So why I talked about qubitization, well, this is now clear, and this is what we know from numerical linear algebra, classical numerical linear algebra, is that Krylov subspaces are essentially can be very nicely described using Chebyshev polynomials. So the Kate Krylov state, if you will call it, will be nothing else as applying the Chebyshev polynomial evaluated on this should be an operator H, the Hamiltonian, sorry. The powers of the Hamiltonian to the to the initial state. So it will be like applying the powers of curly H up to order whatever to your up to order D to your initial state. So that's why we needed qubitization, because I need to be able to do this. And it's essential because those two subspaces are the same. So I don't want to work with these objects because they're too large for being stored. But I can get the same subspace by just applying the Chebyshev polynomial to my initial state. And this I will be able to do whenever I need. And the quantum subspace diagonalization, so this whole projection idea can be used to follow, to get the lowest energy. So that's what we want. And the Chebyshev polynomials will, up to the sampling noise, will give us the equivalent performance. Okay, so we will use the quantum computer here to get the space, the same Krylov subspace that we would get if we would be able to store Lanczos vectors on the quantum computer, and we will do it by utilizing the connection to Chebyshev polynomials. That's the whole idea. The space is the same and the space is essential. And as this is forbidden for us, this is actually something we can target. And if you want more details, Adam is also here. Adam, wave. So Adam is working actively on Krylov subspace methods, so he may give you also a lot of updates. All right, so to diagonalize to bring this big problem into the small, we have to be able to project on the subspace, and the subspace is now defined using the Chebyshev polynomials. We know how to kind of get it through qubitization. So if I look now on the entries of these two small matrices, and that hopefully answers the question that was like, do we have to have the states available and so on? Well, you will realize that we only have initial state, and we have to be able just to apply the Chebyshev polynomial to it to get the entries of the matrix. So how we can now do this? How we can apply the Chebyshev polynomial evaluated on the Hamiltonian or on our operator to the ground state? We will use a number of things. We will use qubitization. We will use the properties of the Chebyshev polynomials. And it turns out that if we look closely, all the calculations are in the paper that I cited at the beginning. These objects that we will actually need boil down to looking on the expectation value of these evaluations of the certain Chebyshev polynomial. So here you have Chebyshev polynomial I plus j plus 1 Chebyshev polynomial, the expectation value. If you do the S, it's very similar. So at the end, you will realize that the only thing you have to be able to do to get those two small matrices is being able to calculate, to determine this object, the expectation value of the evaluation of the kth Chebyshev polynomial for the Hamiltonian. Well, now is the question how to do this, because that's the only thing you need. So we go back to the definition of the block-encoding, or what they called standard form. Remember, standard form was the initial name, and it was a little bit more general than in the block encoding. We always have the M0 qubits at the beginning. Here you allow any kind of equivalence of identity depending what your Hilbert space is. And this is our Hamiltonian. This part may be a little bit fast, but I just want to make sure that the main idea is clear so you can figure out the data. Okay, what we need? We need to block encode and implement this unitary matrix. So this is our unitary matrix that corresponds to the block encoding of our Hamiltonian. This Hamiltonian has Pauli, so this is how you can do it. Any block encoding. This one is in particular simple because of the structure of the Hamiltonian, but you have to be able to do this. Block encode your operator, not a surprise. You also have to be able to prepare the state, and since here you have as I said, in our classical block encoding, this is the object that we have usually is cat 0 tensorized m times. But as I said, you can apply any other because it connects to the rotation with respect to the basis. So that's what, and you can use any existing state perturbation procedure. So you need to block encode, you need unitary representing matrix, you need to be able to prepare your state. So let's assume that we have that at hand. We have the block encoding and we know how to prepare a state. Well, how we are getting those expectations of the evaluation of a Chebyshev polynomial. And then there is this beautiful theorem, which is, I took this exact statement from the paper by Kirby, but I'm not even sure if this is the original source. I didn't find the original source of this, but it may be there. So if you have the block encoding of the Hamiltonian and the state preparation procedure, and you know that your block encoding satisfies this condition, then you can define the reflection around this general G. So remember, when I was talking about qubitization, I simplified it to standard basis. So that R before was this 2 pi minus identity. This was the reflection with respect to the standard basis. But you can do reflection with respect to whatever basis of the Hilbert space you have. This is just more general framework in here. That's why I wanted to talk about it. And then you can get the block encoding of your Kate Chebyshev polynomials using the same idea, the idea of qubitization. You remember there was this R, and this should be UH to the power K, and if you did that, you get essentially in the corner the evaluation of the Chebyshev polynomial. So this object is a block encoding of this. And this is what we have seen in qubitization. It will be easier if I can have the other slide on the side, but this is exactly the object we had before. For simplicity, you can visualize that. Okay, if I have a block encoding of the operator, then my operator is H is sitting here. This RH is now, okay, depending, previously it was 2 by 2 example that I introduced qubitization, so it was 1, -1. But now we have higher dimensions, so there will be an identity matrix of a proper size corresponding to this block, and negative identity matrix on below. And then if I do this, I get my Chebyshev polynomial. And now it gets into really details so if I have this block encoding, I know that I can get a block encoding for my Chebyshev polynomial evaluated on my Hamiltonian. It can be done using the reflection. This whole operator actually can be used depending on the parity. So this is really a construction for this particular Hamiltonian. How you can construct this object when K is even or K is odd. So different K is remember K is the index of the Chebyshev polynomial. And then you define the particular quantities, and it seems that this is what you have to do to get your expectation value, depending of the case even or not. You have the reflection with respect to your basis, and then the block encoding of your Hamiltonian. So there are details about the measurement procedure. So if K is even, if K is odd, which steps you have to repeat to get it. As I said, the result is in a kind of measured, and you have to get it. Remember, this is an expectation value. So how many times you have to run it such that you get enough confidence in the expectation value and so on. So this is the kind of corresponding circuits. If you want to build this circuit, so you see you have this G, which is a transformation around basis. You have the block encoding, the reflection around the basis, and then the measurements, and you measure R or U depending on the parity. So this is the summary of the requirements and the cost associated. T Capital T is connected to the number of Pauli matrix, number of terms in your Hamiltonian. So you see it's very targeted to this particular Hamiltonian. The costs, the measurement overhead, the state preparation, how much it costs, qubit requirements, all those information are there. So here they are just kind of consolidated to presentation. But what I want to talk just briefly is the error analysis of this method. And of course, I have way too much as usual. Sorry. So the error is up to some initial things that we have to skip. Like we have to take into account finite sample noise, device noise, regularization because of the fact that we don't have orthogonal basis. All these conditions are here. And this is the result in terms of ground state energy and estimate. So this is the error in the ground state energy, and it has these different components. You can get all the parameters and so on, but I want to discuss those. So we have a noise rate, we have some delta is constant, we have a threshold for the regularization when you solve the generalized eigenvalue problem. You have to have some estimate on the sum of the eigenvalues which you throw out by regularization. And gamma 0, that was one thing which everyone discussed, the overlap of your initial state with your ground state. It's coming into game. So I want to discuss those components of this error. So the error is proportional to this quantity. So if you look on those quantities, the first part, well, the last component, but I want to start with it. It's error due to exact Krylov space. So it vanishes exponentially with the Krylov space dimension. So that's the classical result that we want to achieve. Since we assume that the space is the same, we want to get this exponential dependence on the convergence rate. The second one is energy error tolerance, and essentially it has these components like what do we know about the spectral gap, how close we are to the other eigenvalues, because if we are too close they will start to come and pollute. If we are well separated, this term essentially can be eliminated. We have error due to regularization that comes from solving eigenvalue, small eigenvalue problem. And there is an additional thing that comes clearly from the way how the proof goes, because the proof followed this paper from actually numerical linear algebra community of analyzing the subspace methods. And the last, I think this is my last slide. Krylov space by dimension depends on these properties. So you have the gap here and the accuracy. And the total number of measurement depends also on the same, the size of the Krylov subspace and the parameters. Again, the gap plays a role, the energy error. So the better the approximation, the more you have to pay. As easy as that. This is the summary, what I have told you. And in order to stay more or less on time, that's all what I wanted to talk. It's really a very dense content, I know. But if you need anything, I try to summarize this. You can always ask me, and I will stop here.
Okay, so questions?
I think I lost everyone.
So I didn't remember the gamma 0 parameter that you have at the very end. Is it the overlap?
So the gamma 0 parameter, yes. So the question is, what is gamma 0? So gamma 0 is overlap between the initial state, so what you start with, and your ground state.
And so then the question is, do you expect on general grounds that you have access to an initial state size 0 that has a large enough overlap with the solution you're looking for?
Yes. So the question is, do we assume that we have? In order for this procedure to work, we need the initial state to have this proper overlap. And there are techniques how to maybe construct those initial states with the large enough overlap for certain Hamiltonians. I think on Monday there was like similar discussion about for other approaches, but yes, in order for that to work, you need this. The other question is how to get it, but yeah.
Okay.
So yes, your initial state has to have this property of the overlap. Otherwise, if it's not good, you will see that you get an error, but it may not be anything close to what you're searching for. And Adam, please yell if I'm missing anything.
To follow up on the question,
Yes.
could you imagine starting from a state which is uniform, doing everything, having something with a big error, and starting with this state that you obtain and repeating until you have something nice?
So I can imagine that. I don't know if that's what it's done. I can imagine that because, for example, in the classical numerical linear algebra, there are methods that also require you to have a pretty good initial guess. So what we often do, we run it first, we get something, and then we take this something and we input, and eventually we get something better. Question is, I don't know if anyone explored that in this setup. Usually, as I said, those algorithms very often come from people, and in particular, Will is also a physicist. So they have, they will look on the Hamiltonians. The insight from physics very often tells them more or less what should be in that initial state. So if we have, if you have any inside information, you should use it. But if we think long term in terms of like black box, I would say that will be a way to do it, like run it, get some very rough estimate, or even running power method. Like pure power method to get initial state. But then, as I said, it's okay if you want the ground state. But Krylov method is an ideal situation. You should be able to get you want to have maybe like first 10 eigenvalues. And then we know how to do it in the classical way. You do deflation and other recycling and so on. We would love to transfer it to the quantum, but I think we are making baby steps at the moment.
Okay, thank you.
So last question.
And if you have further questions, I'm happy to stay on
this is
break.
a question on the Discord channel.
Okay.
So, is Hamiltonian with Lanczos and Chebyshev methods in quantum computer more advantageous than the classical computer?
I mean, okay. So if we have a limitation in size in terms of class, so I will repeat the question. Shall I? Oh, it's okay. So if it's advantage with respect to the classical, it allows us to handle much bigger problems because we don't have to store the basis. So it gives us essentially possibility of doing much bigger problems for which we know, for example, even the size of basis in the classical way is limited. Also, in terms of like quantum chemistry applications, very often even storing a vector. That's why we move also to tensors, so higher dimensional techniques. We cannot even store a single vector, single tensor or something on the classical computer. So there's no way we can use this method without classical Lanczos even because of those higher dimensions. So curse of dimensionality is the term that many of you may know. So the hope is that this will allow us to go much further because it's based on like similar concepts, but it allows us to do things in a different way.
Okay, so let's thank Agnieszka again, and if you have any questions.
Thank you.